English or Hebrew?
English.
Yeah.
So it's a pleasure to introduce Nadav. Nadav is a PhD in the Hebrew University in Jerusalem. He's doing artificial intelligence. Won several awards: the Rothschild Award, Zuckerman, Google Award, and now he's a postdoc in Princeton in the Advanced Institute of Research of Science, right?
Institute for Advanced Study.
Advanced Studies, right? Advanced Studies. All right.
Okay, thanks Samit. Thanks for having me. Before I start, just to get a little bit of a sense of the background, how many people here know how a convolutional neural network looks like? You know. Nobody knows that, how it looks like. Okay, so that's the vast majority here. And so the vast majority here know that deep learning is the best thing ever. Really transforming a lot of application domains, works really, really well. But there's a dark secret to this technology, and that is that we don't really have a clue what's going on. Okay? And many people, including myself, believe that it's important to try to understand why these algorithms work the way they do, what makes them suitable for one problem and not another. There are several reasons for this. One is scientific curiosity. Another one is that technologies that we understand tend to work better than ones that we don't. And even if you don't care about these two, then deep learning is entering application domains which are critical. Infrastructure and health. And the last thing you want is an algorithm that you don't understand, making decisions that you don't understand and costing human lives. Okay, so hopefully we're all convinced that it's important to understand. And what I'm going to start with is kind of a personal perspective on what it means to have a mathematical theory behind deep learning. Okay, this part will be very high level, designed for those of you that are not experts in this area. For those that are, please don't throw cookies or tomatoes or anything at me. I'm going to be very, very high level and inexact. And in the second part, I promise to be more formal. Okay? All right, so if you want to formally reason about deep learning, you have to start with statistical machine learning, because at the end of the day, deep learning is a special case. So we're going to lay out here the basic statistical learning setup. Okay? We have an instance space, X. This is the space of possible objects that we want to infer something about. Okay, so it could be 100 by 100 matrices representing 100 by 100 images. It could be vectors representing sequences, or anything goes here. Y, this is the label space. That's the set of possible inferences that we could assign to instances. So if we are measuring some continuous property of an image, Y could be the reals. If we want to classify to dog or cat, then Y could be the set 1, 2, or anything else. We assume that there's some distribution over labeled instances. Okay, pairs of instances and labels. There is some distribution that characterizes the world. We do not know this distribution, but we assume that it exists. And finally, the last property of the world, or of the problem, is a loss function. And this is a function that intakes two labels and returns a non-negative number that indicates the extent to which they deviate from one another. So if the labels are reals, for example, a reasonable loss would be the squared difference. Okay? The basic statistical learning task is as follows. We are given a training set. Okay, this is a set of m pairs, x, y, I, images, labels, and we assume that these pairs were drawn independently from the world's distribution. Right? Given this training set, we would like to return a hypothesis, also known as a predictor or a classifier. That is a function from instances to labels. And we would like to return a function that minimizes the population loss. What is the population loss? That is the average loss, the average discrepancy between the true label and the prediction when instances and labels are distributed according to the world. This is something that we cannot measure because we don't know D, okay? Even if you put aside computational issues. Basically, if you sweep away a lot of the details, the fundamental approach in statistical learning is the following. Before seeing the training set, we predetermine a hypothesis space. That's a set of functions, a set of classifiers. And given the training set, we return the hypothesis, the function in this space, that minimizes the empirical loss. What is the empirical loss? That is the average loss, not over the world's distribution, but over the training set. Here we just run through the training set and measure the discrepancy between the true label and the predictor. So this is something that, given a predictor, we should be able to compute. Okay? So that's basically the approach. We predetermine a family of functions. Given the training set, we return the one that fits this training set the best, and we hope that it does a good job in the real world. Okay? That hypothesis, that predictor that we return, its quality depends on three fundamental factors. And that's what I'll talk about now. This is an illustration. In gray here, that's the set of all functions, all possible classifiers. And in blue, this is our hypothesis space. That's what we fixed in advance. Okay? F star D, that's the predictor that does the best job in general. That's the one that minimizes the population loss. It has nothing to do with us. It's only a property of the world. Okay? H star D, this is the hypothesis within our space that has the minimal population loss. That's the best predictor within our space. It depends on the world and on our choice of hypothesis space. It doesn't depend on the training set in any way. What does depend on the training set is H star S. This is the hypothesis that minimizes the training error, that has the minimal empirical loss. Okay, so theoretically, this is something that we should be able to find. We could just go through every member of this hypothesis space, measure the empirical loss, and return the minimizer. Computationally, sometimes this is very difficult, and we can only return some approximation. This is what we ultimately return. We care about the population loss of this thing, and as I said, it depends on three factors. Number one, approximation error, also known as expressiveness. This results from the fact that our hypothesis space is finite. It doesn't include all possible functions, and therefore there's no reason for it to be able to capture the perfect predictor. There's some penalty here that comes from the limited representational power. The second source of error is called estimation error, also known as generalization. This intuitively results from the fact that the training set is finite. If it were infinite, then a predictor doing a good job on the training set would probably also do a good job in the real world. In practice, though, the training set is very finite, so you could do a good job on the training set, have a low empirical loss, but have a very high population loss. That means you overfit. Okay? And the last source of error, training error, also referred to as optimization, this again results from the fact that we can't always find the empirically optimal hypothesis. Sometimes we return an approximation. So statistical learning theory in its basic form is about understanding these three factors and how they trade off with one another. And they behave in ways in deep learning that are very different from what we're used to in classical machine learning. Okay, so that's what I'll talk about now. So classical machine learning, this is the point where I usually get tomatoes thrown at me. It's not a well-defined term. You can think of linear models, okay, predictors that map instances to labels linearly. In this setting, problems are framed in a way that the empirical loss minimization, the search for H star S, boils down to what is known as a convex program. That means that it boils down to minimization of some huge function that looks like a big bowl. Okay, intuitively. We know how to minimize functions that look like bowls, and so we are actually able to find H star S. There's pretty much no training error. It all boils down to the estimation error and approximation error. And for these, there's a well-known phenomenon. It has different names. One of them is the bias variance trade-off. What it means, roughly speaking, is that if I expand the hypothesis space, I make it larger, then obviously the approximation error goes down. I can represent more. But the estimation error will go up. I will be more likely to overfit. Okay? I will be more likely to have a good empirical loss but a bad population loss, and vice versa. If I shrink the hypothesis space, the approximation error goes up, but the estimation error will go down. I will be less likely to overfit. Okay, so all in all, I think it's safe to say that the theoretical learning community had a feeling that we have a decent understanding of what goes on here. Okay? In deep learning, the situation is very, very different. It starts off from the fact that now the empirical loss minimization, this search for H star S, boils down to a non-convex program. We're minimizing a function that does not look like a bowl. could have many hills and valleys, very complicated landscape, and it's not so easy to minimize. We know for a fact that this H star S, that empirically optimal hypothesis, is not unique. There are a lot of them. And for some reason that we don't understand, variance of gradient descent, which is a very simple algorithm that just takes small steps in the direction of steepest descent, this type of algorithm somehow reaches one of these solutions. And we don't really understand why. And with expressiveness and generalization, the situation is even more different from what we're used to. And that is that we know empirically that some hypotheses that have a low training error, a low empirical loss, some of them generalize well, so they also have a low population loss, but others don't. Others overfit miserably. And for some reason that we don't understand, on typical problems where deep learning works, the solutions that are returned by gradient descent are often ones that generalize well. They have a low population loss. And maybe most surprisingly is the fact that there seems to not be a bias variance trade-off. You make your model larger, you expand the hypothesis space. Obviously, the approximation error goes down, but it seems that the estimation error goes down too. Larger models generalize better. We see this empirically all the time, and we don't have an explanation for this at present. So I think most people, even the experts here, would agree that we don't really understand what's going on here. And these are the type of questions that I have been interested in for the last few years and am interested in now. And I will talk today about works that address some of these questions. Okay, so after that philosophical opening, any questions? No. Okay, so now it's going to be a little bit more exact. We're going to talk here about optimization. Okay, that's the training error. Okay, so this is based on two papers, one that appeared in the last ICML and another one that will be in the upcoming ICLR. In Princeton, done with Sanjeev Arora, Elad Khazan, and students Wei Hu and Noah Golowich. We are only going to talk about training error right now. Okay? We'll get to approximation error later. We're going to start by kind of reflecting on the popular approach, prominent approach for understanding optimization in deep learning. We're going to argue that it's perhaps not the best approach, and some alternative approach is maybe better, and then we're going to follow that alternative approach and show some stuff. Okay? Okay, so the prominent approach for analyzing optimization in deep learning is based on the geometry of the objective landscape, and specifically on its critical points. That's points where the gradient is 0. You could have different types of critical points. Okay, you could have a local minimum that is good, so the objective is close to the global minimum. You could have a local minimum that is bad. Okay, the objective is much higher than the global minimum. You could have a saddle point that is strict. So there are directions of significant descent, or formally, the Hessian has a negative eigenvalue. Or you could have saddle points that are non-strict. So they are very flat, and if you want to descend, you have to walk a certain distance from that point. Okay, that means that the Hessian does not have negative eigenvalues. Right? So these are the type of critical points that you could have. And a result that was shown by different people in different flavors, but essentially it means the following, is that if your objective does not include bad local minima, and there are no non-strict saddles, then gradient descent is going to converge to a good local minimum, which is pretty much the global minimum. Okay, so this sounds pretty intuitive. There is some legwork to show that this happens quickly, and it depends on the type of algorithm that you use, but essentially this is the result. And motivated by this, different people have studied these two properties, no bad local minima and no non-strict saddles. Okay, if you establish these two properties in a deep learning setting, then you automatically get convergence of gradient descent to global minimum. Okay? So this kind of approach was successfully applied to shallow models. That's models with 2 layers. Okay, people have shown that these two conditions, no bad local minima and no non-strict saddle, these two properties hold, hence gradient descent converges to global optimum. It did not prevail when treating deep models. That's 3 or more layers. Okay? It didn't work. thus far, and there are several reasons for this. First and foremost, property number 2, no non-strict saddles, is false. It's just incorrect. Okay, for example, when all the weights are 0, then all the second derivatives are 0. And there you go, there's a non-strict saddle. Okay, so this approach kind of hits a wall right at the outset. A more general argument against geometric approaches is that we know empirically that optimization for deep networks oftentimes highly depends on the initialization that you use. You can use a certain initialization and you converge very well, or you use a different initialization and you diverge. If you are trying to show that the entire landscape is nice, then you're not going to be able to capture this kind of phenomenon. Okay? In practice, we know that different optimization trajectories lead to qualitatively different results. And if you want to account for this, you have to take into account the details of the algorithm and the initialization. You can't only look at the landscape, okay? Because if you try to show that the landscape is nice as a whole, you're not going to be able to show that some trajectories are much better than others, okay? So this kind of trajectory-based approach was taken by different people, some of them sitting here, was done for shallow models. It's kind of explicit analyses of a specific algorithm training a specific model. We're going to take this approach to analyze arbitrarily deep models, specifically deep linear neural networks. And I will explain what that means. Okay? Okay. We're going to start by showing convergence of gradient descent for linear neural networks. What are linear neural networks? In the deep learning jargon, these are fully connected neural networks with linear activation. In the non-deep learning jargon, that's just matrix multiplication. Okay, the input is mapped to the output through a sequence of matrix multiplications. As an input-output mapping, this thing is linear. But when you run gradient descent over this parametrization, then it is non-convex. It's highly non-convex. And for this reason, this is oftentimes viewed as a surrogate for optimization in deep learning, and this is something that's studied extensively. Okay? The state-of-the-art result is by Bartlett et al. From the last ICML. What they showed is that with linear residual networks, which is a special case where the input dimension and the output dimension are equal, and all the hidden dimensions are equal, when that holds, and all the weights are initialized to identity, and the loss is L2, meaning that it is based on the squared Euclidean difference between the true prediction, between the true label and the prediction. For certain types of data sets, gradient descent efficiently converges to global minimum. Okay, so this is fairly specific. The analysis here is highly specific. It depends on, crucially, on the identity initialization, and it requires certain symmetries that there's no reason for them to hold in practice. And yet, this is the only result that I'm aware of for efficient convergence of gradient descent to global minimum over a deep model. Yeah?
Minimum is unique, or there are many minimums?
So there's a unique objective value, but there are a lot of minimums. It's convergence to global minimum means to one of them. Okay? A word about the efficient here. So there are results that show convergence of gradient descent to global minimum for deep models. These results require the networks to be very, very large. Polynomial, but things like the number of examples to the power of 30. So when I say efficient here, I mean something that we see ourselves running on a computer. Okay, and this is the only result that I'm aware of, and we're going to derive something much more general than this. Okay? We're going to start by looking at gradient flow. Okay, what is gradient flow? This is a continuous version of gradient descent. That's what you get when you take the step size to be very, very small. It's a differential equation. Okay, you move according to a curve in space, and at every point in time, the direction of movement is opposite to the gradient. So if gradient descent is these discrete steps, gradient flow is this continuous curve. This is going to be a stepping stone towards gradient descent. We're going to analyze this and then extend it to this. Right? The reason this is useful is because you can use a lot of mathematical tools. Okay, differential geometry and differential equations, and then you get different ideas that if you work very hard, you can extend to the discrete setting. Okay? All right, so we are looking at trajectories of gradient flow over a linear neural network. All right? The objective has a certain structure, and it is as follows. We start with some loss over linear models. Okay, so this could be L2 loss, or hinge loss, or cross-entropy loss, or whatever. And this loss induces an objective over the linear neural network, an over-parameterized objective. Okay, so what's the objective at the point W1 to Wn? Just take all the matrices, multiply them by one another. You get this end-to-end effective mapping, and plug that into the loss. We are running gradient flow over an object that looks like this. Okay? Here's a definition. We say that the weights W1 to Wn are balanced if the following equality holds. Okay? For every j, for every layer j, Wj plus 1 transpose times Wj times itself. Okay? The weight matrix of layer j plus 1 transpose times itself is equal to the weight matrix of layer j times its transpose. Okay? This is a definition. What makes it somewhat natural is that under popular initialization schemes, this thing either holds exactly or approximately. Okay? So if you initialize weights to be close to 0, then this is approximately met. And if you initialize them to be identity, that residual setting, then this is exactly met. What we show, this is the first result, is that the trajectories of gradient flow preserve balancedness. That means that if you use these popular initialization schemes and the weights are exactly balanced or close to being balanced, and then you run gradient flow, it automatically maintains the balancedness. Okay? Gradient flow does not move arbitrarily in space. It follows certain trajectories, okay, that maintain certain properties. For example, one of the implications of this condition is that the singular values of all the weight matrices are the same. Okay, and we're going to use this property to prove different things. Right? So the first question that we ask is the following. When we run gradient flow over a linear neural network, so the objective looks like this. It's just taking the end-to-end matrix, plugging into the loss. We run gradient flow on this, and we can ask, how does the equivalent end-to-end linear mapping, how does that move in space? Okay? It moves according to some dynamics. Right? It's not the same. These dynamics are not gradient flow over the loss because we did not run gradient flow over the loss. We over-parameterized and ran gradient flow over this thing. So the question is, how does this thing, the equivalent end-to-end model, how does that move in space? And the answer is as follows. If the weights are balanced at initialization, then the end-to-end matrix follows what we call the end-to-end dynamics, and this is what's written here. If you ignore this blue term, this is just gradient flow over the loss. Okay, vec means to arrange a matrix as a vector. It doesn't mean anything if you don't have this term here. But you do have this term. And this term is what is called a preconditioner. Okay, it is something very, very popular in optimization. There are various types of preconditioners. Newton's method is a special case based on second derivatives. And here, this preconditioner has a different structure. We have a closed form expression for it. I'm not going to lay it out here. I will say that intuitively what it does is something along the following. These dynamics are moving the end-to-end model according to some path in space. And at every given moment, the singular directions that are prominent in this end-to-end matrix, these are the directions that the preconditioner is going to promote. It's going to stretch the gradient more significantly in these directions. So in some sense, it kind of reinforces where you are in parameter space. It pushes you stronger in the directions where you've moved more. Okay, so what we see here is that if I take a linear model, and instead of running gradient flow over this thing, I replace it by a linear network, and I run gradient flow over this thing, then I implicitly induced a different algorithm. Okay? Implicitly induced a certain preconditioner that promotes movement in directions already taken. It's some form of an acceleration in the technical sense. It's related to momentum, for those that know. We make this exact in the paper. I'm not going to talk about it here. What I am going to do is use this characterization to prove different things. Okay? starting with convergence to global minimum. So this is the end-to-end dynamics. This is the preconditioner. What we show, I mean, it's a direct implication of the expression we have for this, is that the preconditioner is positive definite, it's full rank, when the end-to-end matrix has full rank. Okay? So if this thing is full rank, these dynamics are going to decrease the objective until the gradient here is 0. That means that the loss is going to decrease until the gradient is 0, or maybe at some point the preconditioner stopped, being positive definite, which means that the matrix became singular. So if you run gradient flow over a linear neural network, the loss will decrease until one of these two conditions happen. Either the gradient of the end-to-end matrix is 0, or the end-to-end matrix is singular. Typically, the loss that people use is convex, not the objective of the linear network, but the original loss. This is every example that I'm aware of, this is convex. And so condition number 1, the gradient being 0, means that you reached global minimum. So if you run gradient flow over a linear neural network and the end-to-end matrix never became singular, you are going to hit eventually the global minimum. Okay, so this is this corollary. If the loss is convex and you initialize the linear neural network such that the weights are balanced and the loss at initialization is smaller than the loss of any singular matrix, so by decreasing the loss you're not going to hit singularity, then gradient flow will converge to global minimum. So we have a convergence result for gradient flow. There's no notion of computational efficiency here because this is continuous. Now what we're going to do is extend this to gradient descent. But basically this is the idea. Okay? Okay. So we had two assumptions on initialization in the result for gradient flow. Number 1, we assume that the weights are balanced. So for every j, the weight matrix of layer j plus 1 transpose times itself is equal to the weight matrix of layer j times its transpose. I may as well write this equality as follows. Instead of saying that these two things are equal, I just say that the norm of their difference is 0. Okay? The second assumption we had is that the loss at initialization is smaller than the loss of any singular matrix, of any matrix that has some singular value which is equal to 0. Now what we're going to do is kind of define discrete versions of these two conditions, and that's going to facilitate the result for gradient descent. Yeah?
Isn't this condition very similar to saying the W times the next W is unitary? It kind of looks like it, no?
No. It implies different things. For example, if you take the SVD of Wj plus 1 and Wj, then the V of one will be equal to the U of the other. They don't need to be unitary at all. Okay.
If this thing is true for every j and j plus 1, actually it's true for any two matrices.
I'm sorry?
J and j. If Wj, if any...
Not exactly, because actually no, because notice that the transpose here is in a different position. And the dimensions wouldn't even necessarily align if it's totally different layers. Okay? So that's a good question. Okay, so let's extend.
But the non-zero singular values would be preserved.
Yes, yes.
And when you say Wj and Wj plus 1, this is for a step in the gradient descent algorithm, or this needs to be solved for all steps but with different products?
So first of all, this condition is on initialization. A result is that this will maintain throughout optimization, but the assumption is going to be on initialization. Okay, so let's extend this. First extension is of the first condition. Instead of requiring the norm to be 0, we allow it to be small, smaller than some delta, and we call this delta balancedness. Okay, so if delta is very, very small, you pretty much recover the condition of perfect balancedness. If it's larger, then it's easier to meet this thing. That's for condition number 1. For condition number 2, we define a discrete version that is somewhat a strengthening of this of the condition. We don't require the loss to be smaller than the loss of any singular W. We require it to be smaller than the loss of any almost singular W. That means the loss needs to be smaller not only than the loss of any matrix with a 0 singular value, but of any matrix with a singular value that's smaller than C. So the larger C is, the harder it is to meet this condition. And if C becomes very, very small, then you get back the condition over here. We call this a deficiency margin of C. Right now, these two things are just definitions. I'm not saying anything about how reasonable they are, nothing. These are just definitions. Okay, is this clear? Okay. Here's the result. For that, we show this specifically for L2 loss. Okay, that's for simplicity. We consider the case where the loss of a matrix W is just the averaged squared Euclidean norm of the difference between the true label and the prediction. And here's the result. If gradient descent over a linear neural network is initialized such that, 1, the weights have deficiency margin C, and they're delta balanced with a delta that scales like C squared, then for any learning rate that scales like C to the 4th, the loss will decrease exponentially fast. It will move like e to the minus constant times t. This is called linear rate convergence. Okay? We have here a result that shows convergence of gradient descent to global optimum over an arbitrarily deep network. Okay, and the convergence is exponentially fast, called linear rate, under 2 assumptions on initialization. Right? Let's say a few words about these assumptions. Number 1, they're both, in some sense, necessary. What do I mean? I mean that if I take this theorem and erase this, or erase this, then it's false. I can show you easily, and not even examples, and they're not even pathological, where things will diverge. Gradient descent over a linear neural network doesn't always converge. It's easy to construct counterexamples. Okay?
But there are examples for convergence to a local, or a local optimum for gradient descent, right? Or even non-convergence.
Not for every initialization. Not for, no. For some initializations, that actually Bartlett and Al have that in their paper too. For some initializations, it's never going to converge. I mean that the loss is lower bounded by something, and it's never going to go beneath it.
So it asymptotes. Diverge goes to infinity.
Okay, so in that example, it asymptotes. You can also construct examples where it goes to infinity. The loss, but there, you give me a learning rate, I will give you the initialization that causes it to explode. If you want something for any learning rate, then I can show you examples where it never goes below something positive. Is that clear?
Yeah, I wouldn't call that diverge.
Okay, so let's not call it diverge. Let's call it fail. Gradient descent fails. Okay, if you want it to hold, if you want some concrete initialization that holds for any learning rate, then it fails. If I'm allowed to change the initialization according to your learning rate, I can make it diverge. Okay, thanks for making that point. Yeah, good thing that we have people here to catch me when I'm cheating. Okay. We also show the following. If your output dimension is 1, meaning it's scalar regression, and you initialize the weights according to some scheme that is similar to what people oftentimes use in practice, but not exactly, call this balanced initialization, then both of these conditions hold with constant probability. And by constant, I don't mean some constant. I mean 0.5 or 0.25. It depends on the setting. And so for output dimension 1, use this initialization with probability 0.5 or more. You will get linear rate convergence to global minimum. Okay? To the best of my knowledge, this is the most general guarantee of efficient convergence of gradient descent to global minimum for a deep 3 or more layer model.
So basically, the delta balancedness seems to be something that roughly holds anyway with current initializations.
Yes.
The main problem is the deficiency margin.
It's the problem of meeting them both. Because you see that the delta depends on the C. If they were independent, it was easy. So on one hand, you need C to be large, so that requires your initialization to not be too small. But on the other hand, that makes it difficult for the balancedness. So that's a good point. Okay, so that was convergence to global optimum, and now we're going to show something that I think is more.
You said that the balance is preserved.
Yes. Yeah.
So along the chain, the singular values are approximately the
Yes.
same. But do they change from iteration to iteration?
Definitely.
Does the rank change?
So That's a good point. Does the rank change or do the singular values change? They change drastically because they move to the global optimum. So take the singular values of the global optimum. The nth root will be the singular values of the individual weights when they reach that. So it's changing drastically. Okay, so now we're going to see something that I think is more maybe interesting. That is, we're going to look at the effect of depth. Okay, so the conventional wisdom is that depth boosts the representational power in deep learning. Okay, by adding layers, you can represent more. We all, or many of us, know these illustrations. The first layers can capture these simple shapes, Gabor filters. Then as you move deeper inside the network, your layers can capture more abstract concepts. This is actually formalized, and I'm going to talk about this. You can derive formal evidence that depth boosts expressiveness. What people also believe is that this comes at a price, and optimization now becomes more difficult. Problems that were convex when I used a single layer model, a linear model, become non-convex. And we don't like non-convexity. Okay, so it makes it harder. What we're going to see is that this is not always the case. Okay? For the case of linear neural networks, we derive these end-to-end dynamics. That's this implicit preconditioner. This is for gradient flow. And if you consider the discrete version for gradient descent, it looks like this. Just the same. You have discrete steps, and you have this preconditioner. What we show is the following. For any p greater than 2, there exist settings where L, the loss, is the LP loss. That means that it is the average p norm to the power of p of the difference between the true label and the prediction. Okay? So if p equals 2, this is the L2 loss. If p equals 4, this is L4 loss. It's convex for any p greater than 1. Okay? So there exist settings with this loss where these dynamics, the end-to-end dynamics, reach the global minimum much, much faster than gradient descent. So theoretically, we know that there exist settings where instead of running gradient descent over a linear model with a convex problem, you replace that linear model by a linear network, a deep linear network. Doesn't give you anything in terms of expressiveness, and yet it accelerates optimization significantly. Okay? The way we prove this is by kind of carefully constructing these ill-conditioned cases where gradient descent fluctuates wildly and the end-to-end dynamics somehow avoid this. So this is kind of surprising. It's a theoretical result. It's an existence result. So one could say that this is all nice, but why should this be relevant to practice? I kind of adversarially constructed a data set that makes this happen. And for that, we run experiments. Okay? So these are experiments with linear neural networks. We took a regression problem, the biggest one we could find from UCI Machine Learning Repository, and we use L4 loss. Okay? This is the result of running gradient descent over a one-layer model. So the blue is a convex problem. In green, that's gradient descent over a two-layer model. And in red is gradient descent over a three-layer model. And you can see that artificially non-convexifying the problem, okay, without gaining anything in terms of expressiveness, accelerated optimization significantly in this case. And it actually happened every time we tried with L4 loss. This is what happened. Okay, so this is something that's fairly non-intuitive. Yeah?
What time per iteration would be?
That's a great question. So first of all, in this specific case, the output dimension is 1, and every layer is just a scalar. So it's negligible completely, the addition. I can show you that it doesn't really matter if they were wider. And we actually see that in theory too. Specifically in this plot, the added price in computation is 0, pretty much. It's just another scalar. Okay?
What happens if you increase into the
It doesn't matter. In the linear nets, it doesn't matter. It only matters if one of them becomes narrower than the input or the output, which makes you rank deficient. In that case, it does matter. Other than that, it doesn't matter. We actually show that in the paper, too, and it doesn't matter. It's pretty surprising, but in the case of linear nets, it doesn't matter.
Does it match that to a known algorithm for the convex case?
Definitely. That's what I've written down. Yeah. Yeah. And we actually compared the gradient descent over a deep network to that to an explicit implementation of that implicit algorithm, and it's the same. And the next thing we did was compare this implicit acceleration of depth to explicit acceleration methods, specifically eta grad and eta delta. You can see that in this case, the implicit acceleration of non-convexity outperforms explicit acceleration methods that were designed for convex problems. Okay, so this is pretty surprising. People work very hard to develop these methods to accelerate convex problems, and terrible non-convexity actually is a good thing in this case, and it works better than these methods. Okay?
Let's say 4/n2, then
It's not going to be faster, no. It's going to be pretty similar, a little bit slower. It matters, yeah. So in the theory, we needed that, and actually in practice, we saw it too. Okay, so that's a different question. Who the heck needs L4 loss? So first of all, that's not what I'm trying to argue here, but you could say that maybe you want a loss that's flat around the minima or something like that. Yeah.
Classification losses, like
Okay, so that's the next slide. So this is an experiment for nonlinear nets. Here, it's not backed by theory. It's just taking the same idea and applying to a nonlinear net. We took the convnet convolutional network that's built into TensorFlow for MNIST. Okay, for those that know, there are convolutional layers, ReLU activation, max pooling, and you have two dense layers separated by ReLU. And the training is with stochastic gradient descent with momentum and dropout. For those that are unfamiliar with these terms, it really doesn't matter. Okay? What we did is we over-parameterized by adding linear layers after every dense layer. So again, we don't change expressiveness. We just replace this matrix by a product of two matrices. Okay? So we add, in this case, 15% in the number of parameters. We don't change anything in terms of expressiveness. And in this case, this is what happens to the loss. This is very, very significant. This is, to be honest, this is the most drastic improvement we saw, so that's why I'm showing it here. But we saw improvements in pretty much every setting that we tried here. So no gain in expressiveness, 15% in number of parameters, making the problem seemingly more complicated, makes stochastic gradient descent accelerate significantly. Yeah?
what is the effect on generalization?
So they behave the same in this case, but that's an empirical observation. It went down faster too.
Because this acceleration, because it is known that some algorithms that make you converge faster generalize well.
I agree.
So Adam, for example, that's
I completely.
so the question is whether adding the parameters here.
So I'm saying, in this case, it went down faster. That's not something that I could argue theoretically. We just saw it here. The point I'm trying to make is,
This is trained here.
but I'm not plotting test error. I'm telling you that the test error moved accordingly. Okay? It's not something that I can explain right now, but that's what happened there. I don't know if Lior is here. No? So I'm glad he's not, because he wanted to force me to put an extra slide this morning. He just told me that he saw a follow-up of this work that shows this phenomenon in much larger scale settings. Okay, so I'll have to read that paper and get back to you what exactly they do, but they use this idea for real settings. Okay? All right, so we're close to finishing. Now I will spend about 5 minutes on expressiveness. I gave a talk about this last year. Full hour spent on this. I'm sure everyone here remembers, so I'm not going to spend a lot of time on this. This is based on a long series of papers done at the Hebrew University with Amnon Shashua, my PhD advisor, and students. Here we focus only on approximation error, only on expressiveness. Okay? So when considering optimization, we talked about linear neural networks, and they can be thought of as a matrix decomposition. I'm representing an end-to-end matrix as a sequence of matrix multiplications. And in the graphical language of decomposing multidimensional arrays, this thing is plotted this way. We have two outgoing edges, that's the overall matrix, and every node here is a parameter matrix. This kind of language can describe not only matrix decompositions, but tensor decompositions too. I can decompose high-dimensional arrays, and I can do it with different types of topologies. Okay, for example, a tree or a train structure. And what we have shown is that just like linear neural nets correspond to matrix decompositions, Tensor decompositions correspond to other types of networks. Okay, so for example, a tree decomposition, that corresponds to a convolutional network. And a train decomposition corresponds to a recurrent network. For those that don't know, this is pretty much the golden standard for image applications, and this is very, very popular in text processing. These kind of networks that are equivalent to tensor decompositions are not exactly the models that are most frequently used in practice. They're arithmetic neural networks. Okay? That means that all the nonlinearities come from products. These are kind of polynomial networks, polynomial models. Okay? Hierarchical tensor decompositions, these are some objects that are well studied in different areas of mathematics and also in quantum physics. And what we did is we adopted tools from these domains, and we also proved new results to study the expressiveness of arithmetic convolutional networks. Okay? Some of the things we've shown are the following. Almost every function realized by a deep model requires a shallow model to have exponential size. So if I randomize the weights of a deep model by some continuous distribution, doesn't matter which, with probability 1, I get functions that I can't even approximate with a shallow model unless it's exponentially large. Okay? Other results that we've shown, for example, are that if you have a convolutional network classifying an image and you make your deep layers, the layers further down the road, you make them wider, then you enhance the network's ability to model correlation between pixels that are far apart in the image space, I mean geometrically. And if you make your early layers wider, then you help modeling correlation between pixels that are nearby, that are adjacent. We also showed that, for example, in the pooling geometry of the convolutional network, pixels that are pooled together early can have stronger correlation. Okay, so these two results actually induce concrete guidelines for how to design a convolutional network in accordance with something you know on a task at hand. And we demonstrated this empirically. For example, in a medical imaging task, when you want to detect symmetry, and then you care about correlations between reflections, we've shown that you can design the pooling geometry and the widths of hidden layers in your network, and it, according to these guidelines, and it actually boosts performance significantly. Okay, so that was really in a nutshell. Other people have built on this framework to study many more aspects of expressiveness of both arithmetic convolutional networks and recurrent models. This is just a sample of works from the last year. Okay? And that was the recap on expressiveness. And now let's go ahead towards conclusion. So understanding deep learning calls for addressing 3 questions: expressiveness, optimization, and generalization. We talked about optimization. We argued that the landscape approach can't treat deep models, that's models with 3 or more layers, and that if you want to do this, you have to take into account the specific trajectories taken by the optimizer. We did this for gradient descent over deep linear neural networks. We derived what is, to my knowledge, the most general guarantee for convergence of gradient descent to global minimum over a deep model. Okay? And more surprisingly is that, in this case, depth induces a preconditioner that can accelerate convergence even when you don't gain anything in terms of expressiveness, and despite the fact that you introduce non-convexity. For expressiveness, I didn't show, I more or less told you that just like linear nets are equivalent to matrix decompositions, arithmetic nets, arithmetic neural nets, are equivalent to tensor decompositions. And then you could adopt tools from different areas of math and quantum physics to prove different results on their expressiveness. Okay? And a note about arithmetic neural networks is that they're not just theoretical entities that are easier to analyze than standard deep learning models. These things actually work well in practice. We have implementations of them in Caffe and TensorFlow. Okay, they're online. You can see them here. We showed that it reaches more than 90% on CFAR. For those that know, this is where the state-of-the-art of deep learning was maybe, 4 years ago or something. Way, way better than anything that's not deep learning. And we also show that for different types of tasks, for example, if you're classifying and you suddenly have missing data, these kind of models could actually give you state-of-the-art performance. And this all leads me to believe that there's nothing sacred about the exact tricks of the trade that people use today. And we know for a fact that different variants and different types of architectures reach roughly similar results. And arithmetic neural nets are a case that demonstrates this. They work comparably to the state-of-the-art of contemporary deep models. Okay, it's not state-of-the-art, maybe because we're not as good as engineers as Google and NVIDIA are. Maybe if they decided it's important, it will be state-of-the-art. But at least in my view, they definitely capture the essence of deep learning. And so my goal has been for the last few years and is today to understand the expressiveness, optimization, and generalization of arithmetic neural nets. Here's a toy roadmap to get there. Okay, this is linear neural networks. They're matrix decompositions. This is kind of a toy alpha model of arithmetic neural networks, which are tensor decompositions. We have expressiveness, optimization, and generalization. Expressiveness for linear neural nets, it's trivial. It's just linear. Optimization, however, is not, and that's what we spend most of the time on. We have a footstep here. Don't understand everything, but we've begun. Expressiveness for arithmetic neural nets, that's what I briefly summarized to you. We have a footstep here too. Optimization for arithmetic neural nets, this is something that we are working on now. Basically, the idea is to take results that we derived for gradient flow over matrix decompositions and extend them to gradient flow over tensor decompositions. And some of the properties transfer. For example, balancedness. There are different types of balancedness that are going on there. Another box here that we're exploring is generalization for linear neural nets. Okay, so Ishai can tell you all about this. We're considering a case of matrix completion, where you observe a small number of entries and you want to complete the matrix. The ground truth is some low rank model. And what you do is you instantiate a linear neural network and just run gradient descent over that. Apparently it induces some particular regularization, which we have a closed form expression for. And overall, I'm hoping the next 2-3 years or something to have a footstep in all these three anchors and have a deep learning model that we understand much better than the models that most people use, and yet it captures the essence of deep learning empirically. I think that would be a step forward. And kind of looking farther ahead, everything I talked about today falls into the category of theory for supervised learning. And in supervised learning, theory is way, way behind practice. Okay, things work very well long before we understood them. We actually still don't. But if you want to get to strong AI, human-level AI, whatever that means, then supervised learning is not all there is to it. There are settings that much more closely resemble humans. For example, semi-supervised learning, where many of the examples that you see don't have labels, and you still want to be able to extract information from them. Okay, when you teach a child what a dog is, and you show him or her 10 examples of a dog, and you tell him or her that it's a dog, and then they see a lot of other dogs without anyone telling them that it's a dog, and they still learn from this. Right? A more elaborate setting is reinforcement learning or control, and this is where you want a model that not only passively tells you what it thinks an image contains, it actually operates in a dynamic environment. And this is a very general setting. We are reinforcement learning agents in some sense. Okay, and in these two settings, the practical success is nowhere near where it is for supervised learning. I think most people would agree. And I believe that maybe the next big leap will come from some theoretical understanding or theoretical insight. And I believe that in order for this to happen, we will need to adopt tools that we're not necessarily used to in statistical learning, tools from other scientific areas. I'll give here a couple of examples. In semi-supervised learning, so hierarchical tensor decompositions induce certain probabilistic models, graphical models, and they can be used to model distribution of data. We use this for the classification and missing data that I showed you before. It could also be used for semi-supervised learning. That's something that we're thinking about now. And for reinforcement learning, these days, model-based RL, that means cases where you have a model for the environment, typically works. I mean, the success stories that we know of are model-based. Model-free reinforcement learning, the success is more limited. And one of the problems is that, okay, so we know how to model the game of Go. That's easy. But how do you model a generic environment? We don't have a way to do this. And I think there's a lot we can learn from physics, and specifically from the way that they characterize physical states. Okay, they have laws and computational tools relating to correlations and time evolution and things like that. And some of them we've adopted for studying expressiveness, okay, dependencies between pixels that I talked about. And I believe that we can also perhaps try and use them to model physical reinforcement learning environments that are general enough to capture various problems. Okay, and these two examples, they kind of point to something more general, which is assumptions and modeling. In classic machine statistical learning, we typically don't like making assumptions. We like results that are distribution independent and are general. But that ultimately leads one to consider worst case analyses. And we know for a fact that things that work in practice are guaranteed to fail in the worst case. And that means that we will have to introduce extra assumptions and more modeling. And I, again, think that we will need to turn to tools that we're not necessarily used to in statistical learning. And I anticipate that this will be a key factor in our road to strong AI. So with that, I'll conclude. Thanks. Okay, thanks.